To determine the service conductor load for a commercial building with multiple tenants, it's crucial to understand that this is different from the total service load. The service conductor load represents the sum of the maximum demand loads for each individual tenant, and it's this value that dictates the appropriate size of the service conductors. Let's break down the process. Firstly, identify all the electrical loads for each tenant. These loads typically include heating, air conditioning, refrigeration, water heaters, show window lighting, receptacles, microwave ovens, signs, and motors. Secondly, calculate the volt amps for each of these loads. Remember that volt amps is the product of voltage and amperage. For resistive loads like heating and water heaters, the volt amps is usually equivalent to the wattage. For motor loads, you'll need to refer to the motor's nameplate to find the full load amps or FLA, and then multiply that by the voltage. Thirdly, apply any applicable demand factors or diversity factors. These factors recognize that not all loads will be operating at their maximum simultaneously. The National Electrical Code, or NEC, provides guidance on demand factors for various types of loads. For example, receptacle loads often have a demand factor applied, reducing the overall load calculation. Fourthly, calculate the maximum demand load for each tenant. This involves summing up all the individual loads for that tenant after applying any relevant demand factors. It's important to consider any large motor loads separately, as the NEC often requires special treatment for the largest motor in the group. Fifthly, sum the maximum demand loads for all tenants. This gives you the total service conductor load in volt amps. Sixthly, divide the total service conductor load in volt amps by the service voltage to obtain the service conductor load in amps. This is the value you will use to select the appropriate size of service conductors. Let's consider a practical example. Imagine a commercial building with two tenants. Tenant 1 has a 10,000 volt amps heating load, a 12,420 volt amps receptacle load, a 3,000 volt amps microwave, a 2,400 volt amps sign, a 2,880 volt amps motor, a 8,000 volt amps water heater, a 12,400 volt amps show window lighting load, and a 21,600 volt amps air conditioning unit. Summing these loads gives us a total of 72,700 volt amps. Tenant 2 has a 30,000 volt amps welding load accounting for a 50% duty cycle, 11,210 volt amps receptacle load, a 3,000 volt amps microwave, a 2,400 volt amps sign, a 13,440 volt amps motor load, a 1176 volt amps motor, a 12,000 volt amps motor, and a 65,000 volt amps air conditioning unit. Summing these loads gives us a total of 138,226 volt amps. The service conductor load is the sum of these two values, 72,700 volt amps plus 138,226 volt amps, which equals 210,926 volt amps. If the service voltage is 240 volts, then the service conductor load in amps is 210,926 volt amps divided by 240 volts, which equals approximately 879 amps. A few important considerations. Always consult the latest edition of the NEC for specific requirements and demand factors. The NEC provides detailed tables and guidelines for calculating service loads. Pay close attention to motor loads, as they often require special calculations due to their high inrush currents. Consider the potential for future expansion when sizing service conductors. It's often prudent to oversize the conductors slightly to accommodate future load growth. Ensure that all electrical work is performed by qualified and licensed electricians. Electrical work can be dangerous, and it's important to follow all safety precautions. In summary, calculating the service conductor load involves identifying all electrical loads, applying demand factors, summing the individual tenant loads, and dividing by the service voltage. This value is critical for selecting the appropriate size of service conductors and ensuring a safe and reliable electrical system. Let's delve a bit deeper into some of the specific load types and how they're handled in service calculations. Firstly, heating and cooling loads. For heating loads, the volt amps is typically equal to the wattage unless it's a non-resistive heating element. For air conditioning loads, it's important to use the nameplate volt amps rating of the unit. In some cases, the NEC allows you to use a smaller demand factor for air conditioning loads, especially when there are multiple units. Secondly, receptacle loads. Receptacle loads are often subject to demand factors, as it's unlikely that all receptacles will be in use simultaneously. The NEC provides tables that specify the demand factors for receptacle loads based on the type of occupancy and the number of receptacles. Thirdly, lighting loads. Lighting loads are calculated based on the volt amps per square foot, as specified in the NEC. The volt amps per square foot varies depending on the type of occupancy. For example, office buildings typically have a higher volt amps per square foot requirement than storage facilities. Fourthly, motor loads. Motor loads require special attention due to their high inrush currents. The NEC requires you to calculate the full load current of each motor, and then apply a factor based on the type of motor and its duty cycle. The largest motor in a group often requires a higher factor than the other motors. Fifthly, electric vehicle charging equipment. With the increasing popularity of electric vehicles, it's important to consider the load imposed by electric vehicle charging equipment. The NEC provides specific requirements for calculating the load of electric vehicle chargers. Always consult the latest edition of the NEC for the most up-to-date requirements. Sixthly, other loads. Other loads such as cooking equipment, data processing equipment, and medical equipment should be calculated based on their nameplate ratings. Demand factors may apply to some of these loads depending on their type and usage. Let's talk about demand factors. A demand factor is a ratio of the maximum demand of a system, or part of a system, to the total connected load of the system, or part of the system under consideration. The demand factor is always less than 1. A demand factor of 0.8 means that only 80% of the connected load is expected to be in use at any one time. Demand factors are used to reduce the calculated load and thereby reduce the size of the conductors and overcurrent protection devices. The NEC provides demand factors for various types of loads, including lighting, receptacles, cooking equipment, and motors. It's important to use the correct demand factors for the specific application. Demand factors are typically based on statistical data and engineering judgment. They take into account the diversity of loads and the fact that not all loads will be operating at their maximum simultaneously. The use of demand factors can result in significant cost savings, as it allows you to use smaller conductors and overcurrent protection devices. However, it's important to use demand factors judiciously and to ensure that the calculated load is sufficient to meet the actual demand of the system. If the calculated load is too low, the system may be overloaded, which can lead to overheating, voltage drop, and equipment failure. Let's talk about diversity factors. A diversity factor is the ratio of the sum of the individual maximum demands of the various subdivisions of a system to the maximum demand of the entire system. The diversity factor is always greater than 1. A diversity factor of 1.2 means that the maximum demand of the entire system is only 83.3% of the sum of the individual maximum demands of the subdivisions. Diversity factors are used to account for the fact that the maximum demands of the various subdivisions of a system do not all occur at the same time. The NEC does not explicitly define diversity factors, but they are implicitly used in some of the load calculation procedures. For example, the NEC allows you to reduce the calculated load for electric ranges in dwelling units based on the number of ranges. This is effectively a diversity factor. Diversity factors are typically based on statistical data and engineering judgment. They take into account the fact that the maximum demands of the various subdivisions of a system are not perfectly correlated. The use of diversity factors can result in significant cost savings, as it allows you to use smaller conductors and overcurrent protection devices. However, it's important to use diversity factors judiciously and to ensure that the calculated load is sufficient to meet the actual demand of the system. If the calculated load is too low, the system may be overloaded, which can lead to overheating, voltage drop, and equipment failure. Demand factors and diversity factors are related concepts, but they are not the same thing. A demand factor is applied to a specific load, while a diversity factor is applied to the entire system. Demand factors are always less than 1, while diversity factors are always greater than 1. Both demand factors and diversity factors are used to reduce the calculated load, and thereby reduce the size of the conductors and overcurrent protection devices. However, it's important to use both demand factors and diversity factors judiciously and to ensure that the calculated load is sufficient to meet the actual demand of the system. Let's talk about voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance. Voltage drop can have a significant impact on the performance of electrical equipment. Excessive voltage drop can cause motors to overheat, lights to dim, and electronic equipment to malfunction. The NEC recommends that voltage drop should not exceed 3% for branch circuits and 5% for feeders. To calculate voltage drop, you need to know the length of the conductor, the current flowing through the conductor, and the impedance of the conductor. The impedance of the conductor depends on its material, size, and temperature. The NEC provides tables that list the impedance of various types of conductors. To minimize voltage drop, you can use larger conductors, shorter conductor lengths, or conductors with lower impedance. You can also use voltage regulators to compensate for voltage drop. Let's talk about short circuit current. A short circuit is an abnormal condition in an electrical circuit in which current flows through an unintended path with very low impedance. Short circuits can be caused by insulation failure, accidental contact between conductors, or equipment failure. Short circuits can result in very high currents, which can cause damage to equipment, fires, and electric shock. To protect against short circuits, you need to use overcurrent protection devices such as fuses and circuit breakers. The overcurrent protection devices are designed to interrupt the flow of current when it exceeds a certain level. The interrupting rating of an overcurrent protection device is the maximum short circuit current that it can safely interrupt. The interrupting rating of the overcurrent protection device must be greater than the available short circuit current at its location. The available short circuit current depends on the source impedance, the transformer impedance, and the conductor impedance. To calculate the available short circuit current, you need to perform a short circuit study. A short circuit study is a detailed analysis of the electrical system that determines the available short circuit current at various points in the system. Short circuit studies are typically performed by qualified electrical engineers. Let's talk about grounding. Grounding is the connection of an electrical circuit or equipment to the earth. Grounding provides a low impedance path for fault current to flow back to the source, which helps to protect against electric shock. Grounding also helps to stabilize the voltage of the electrical system. The NEC requires that all electrical systems be grounded, with a few exceptions. The grounding system consists of a grounding electrode, a grounding electrode conductor, and equipment grounding conductors. The grounding electrode is a metal rod, pipe, or plate that is buried in the earth. The grounding electrode conductor connects the grounding electrode to the neutral point of the electrical system. Equipment grounding conductors connect the metal enclosures of electrical equipment to the grounding system. To ensure effective grounding, it's important to use the correct size and type of grounding conductors and to make sure that all connections are tight and corrosion resistant. Let's talk about bonding. Bonding is the connection of metal parts of an electrical system to create an electrically conductive path. Bonding helps to equalize the voltage between metal parts, which reduces the risk of electric shock. The NEC requires that all metal parts of an electrical system be bonded, including metal conduits, metal enclosures, and metal equipment. Bonding is typically accomplished by using bonding jumpers, which are short lengths of conductor that connect the metal parts together. To ensure effective bonding, it's important to use the correct size and type of bonding jumpers and to make sure that all connections are tight and corrosion resistant. Let's talk about surge protection. A surge is a transient voltage that is significantly higher than the normal operating voltage. Surges can be caused by lightning, switching of electrical equipment, or other disturbances on the power system. Surges can damage or destroy electronic equipment. To protect against surges, you can use surge protective devices or SPD. SPD are designed to divert surge current to ground, thereby protecting the equipment connected to the electrical system. The NEC requires that SPD be installed in certain locations, such as service entrances and panel boards. SPD are available in a variety of types and sizes, and it's important to select the appropriate SPD for the specific application. Let's talk about harmonics. Harmonics are sinusoidal voltages or currents having frequencies that are integer multiples of the fundamental frequency. Harmonics are typically caused by nonlinear loads such as electronic equipment, variable frequency drives, and arc furnaces. Harmonics can cause a variety of problems in electrical systems, including overheating of equipment, increased losses, and malfunction of electronic equipment. To mitigate harmonics, you can use harmonic filters, which are designed to block or reduce the flow of harmonic currents. Harmonic filters are available in a variety of types and sizes, and it's important to select the appropriate harmonic filter for the specific application. Let's talk about power factor correction. Power factor is a measure of how effectively electrical power is being used. A power factor of 1.0 means that all of the electrical power is being used to do useful work. A power factor of less than 1.0 means that some of the electrical power is being wasted. Low power factor can be caused by inductive loads such as motors and transformers. Low power factor can result in increased losses, reduced capacity, and higher utility bills. To improve power factor, you can use power factor correction capacitors, which are designed to compensate for the inductive reactance of the load. Power factor correction capacitors are available in a variety of types and sizes, and it's important to select the appropriate power factor correction capacitor for the specific application. Let's consider some common mistakes when calculating service conductor loads. Firstly, forgetting to include all loads. It's important to carefully identify all electrical loads in the building, including lighting, receptacles, heating, cooling, motors, and any other equipment that draws power. Secondly, using incorrect demand factors. The NEC provides specific demand factors for various types of loads. It's important to use the correct demand factors for the specific application. Thirdly, neglecting motor loads. Motor loads often require special calculations due to the high inrush currents. It's important to follow the NEC requirements for calculating motor loads. Fourthly, ignoring voltage drop. Voltage drop can have a significant impact on the performance of electrical equipment. It's important to calculate voltage drop to ensure that it does not exceed the NEC recommended limits. Fifthly, failing to consider future expansion. It's often prudent to oversize the service conductors to accommodate future load growth. Let's talk about safety. Electrical work can be dangerous. It's important to follow all safety precautions when working with electricity. Always to energize circuits before working on them. Use appropriate personal protective equipment, such as rubber gloves and safety glasses. Never work alone. If you are not qualified to perform electrical work, hire a qualified electrician. Let's talk about the importance of documentation. It's important to keep accurate records of all electrical calculations and installations. This documentation can be useful for troubleshooting problems, planning future expansions, and complying with regulatory requirements. The documentation should include the following information: load calculations, wiring diagrams, equipment specifications, and inspection reports. Let's summarize the key steps in calculating service conductor loads. Firstly, identify all electrical loads. Secondly, calculate the volt amps for each load. Thirdly, apply demand factors. Fourthly, sum the individual tenant loads. Fifthly, divide by the service voltage. Sixthly, select the appropriate size of service conductors. Remember to consult the NEC for specific requirements and demand factors. And always prioritize safety when working with electricity. By following these steps, you can accurately calculate service conductor loads and ensure a safe and reliable electrical system.